Good day, class. Today we're going to be talking about the applications of the JK flip-flop in frequency division and counting. So first, let's focus on it being a frequency divider. So you can see that this is the first JK flip-flop, this is the second, and this is the third. You can see the clock signal goes into the clock input of the first JK flip-flop. Now, the output of the first JK flip-flop acts as the clock for the next JK flip-flop. You see how important this is when I draw out the output waveform. Please notice that these circles mean NGT. It means the flip-flop only changes signal at an NGT, negative going transition of the clock. And you can see the output of the second JK acts as the input to the next clock or the next JK flip flop. So this is how this works. Now let me show you the output, how this will look like at the output waveform. So this is our NGT. We have drawn our lines at the NGT of our clock. Now first let's draw for Q naught here. So for Q naught, let's draw our output waveform. We know since this is a JK flip flop and if J is equal to 1 and K is equals to 1, Q is going to toggle. It's from the truth table. So J is 1 here and K is 1. So we're going to be toggling at every NGTC. So assuming we are starting at Q naught equals to 1 because we're starting from this first JK flip flop over here. So we're going to come, this is the first NGT we made. We're going to toggle Q because J equals 1, K equals 1. Till we meet the next NGT, we're going to toggle again, we're going to toggle again, and we keep going to reach the end. So at every NGT you meet, you toggle Q. And that is for Q naught. Now, I told you that the Q naught acting as the input clock for the next JK flip flop will affect it. So now, since we know that this JK flip flop, this second JK flip flop, only replies to NGT, we're going to look for the NGTs of our Q naught because it's acting as the clock signal for the next JK. Sorry, I've drawn it wrong. Sorry for my mistake. We're going to draw our arrows at the NGT. We're going to draw arrows at this point, at this point, at this point. Yes, that will be all. So now let's draw our Q1, that is our second JK flip flop. Since it's using Q naught as its clock signal, we're going to start as Q1 initial is 1. Now we're at the first NGT here. We're going to toggle Q because J equals 1 and K is equals to 1 at this point as well. So we're going to toggle Q. So let's toggle. At the next NGT, we'll toggle Q again. Let's start from here again. You keep Q 1 0 till you get to the next NGT. Now at the next NGT, we're going to toggle to get to the next NGT. At this NGT, we're going to toggle again till we get to the next NGT. We're going to keep going like that till you reach. Yes. And this is the last toggle. Now you can see this waveform of Q1 is quite different from the waveform of Q0. This brings us to the concept of frequency division. So the clock pulse has a frequency of 100 Hz. Q0 is going to divide that frequency. Flip-flops divide frequency by 2. So at this point, we're going to have 50 Hz. Now, at this point, we're going to have 50 Hz divided by 2, which is going to be 25 Hz. And as you can see, it's very obvious from the diagram that the frequency is dividing because of how the spacing has increased for Q1 in comparison to Q0. Now, if you're to draw for the last flip-flop, that is Q2, I'm drawing with a different pen so we can see this clearly. We're going to use Q1 as our clock signal now. So we draw arrows at where we see our clock signal, like NGT. Now, assuming Q2 is equals to 0 initially, We have reached our first NGT. At this point, we know that for Q2, J is 1 and K is 1. So Q will toggle at each point. So let's start toggling Q2. At this, we have met our first NGT. We're going to toggle till we reach our next NGT. Now at this point, we're going to toggle Q2 again till we reach our next NGT. At this point, we're going to toggle till there's no other NGT left. So from the diagram, we can see that the frequency has been divided again by 2, which is 12.5 Hz. So this is the application of flip-flops in frequency division. So another way to look at frequency division is initially frequency is 100 Hz. The first JK flip-flop, which is it, divides the frequency by 2 to the power 1, which is 50. The next JK flip-flop divides that frequency by 2 to the power 2, which is 100 over 4, is equals to 25. And the last flip-flop divides the frequency by 2 raised to power 3. Sorry, it's going to give us 100 divided by 8, which is equals to 12.5 Hz. So this is how the JK clock flip-flop can be used in frequency division. Now looking at the second application of the JK flip-flop in the case of the counting operation. So we have our three JKs Q0, Q1 and Q2. And we have our clock pulse coming in as shown in our diagram over here. These are our clock pulses. Now at the first clock pulse, we're going to have 1 0 0. In decimal, this is 1. In the second clock pulse, we're going to have 0 1 0. In decimal, this is 10. We're going to continue like this till we reach 7 and then we reset. I will explain to you why we have to reset after 7. This should be 1 0 0. This is the fourth clock pulse. At the fifth clock pulse, we're going to have 1 0 1, which is 5 in binary. In decimal, this at the sixth clock pulse, we're going to have at the seventh clock pulse, we're going to have. Now after this, at the 8 clock pulse, everything is going to reset. Now let me explain why everything resets at the clock pulse. This particular flip-flop only has 3 flip-flops in it. That's 3 inputs. So 2 raised power 3 is 8. So this is an 8, mod counter, or rather a mod 8 counter. And a mod 8 counter means it can count up to 8 different states. Or rather, it can count 8 different states, which is going from 0 to 7. If you count from 0 to 7 with your fingers, you're going to see that you're going to get 8 different numbers. So after 7, there's nowhere else to go. So the flip-flop is going to reset back to 0 again and start counting to 7. Similarly, just to draw the point home, if you have 4 flip-flops, we're going to have 2 raised to power 4. It's going to be a 16 mod counter, or mod 16 counter. It's going to have 16 different states. That is going from 0 to 15. So after 15, the flip-flops are going to reset to 0. So that's just point. So let's come back to this table. At the 8th pulse is reset. And it starts from 0 0 1 again at the 9th pulse. And you keep going again, reset when you reach your maximum. So that is how the JK flip-flops can be used for counting. So you can see we counted from 1 to 2, 1 to 3, 1 to 3, 4, 5, 6, 7, 8. Then you reset 1, 2, 3, 4, 5, 7, 8. So you're able to count up to 8 different states. You're able to count 8 values. So if you have It's if for instance apples you want to count that are passing through a counter, you can use three JK flip flops to do this. Similarly, if you have up to 16 items you want to count, you can use four JK flip flops to achieve that. That is how the JK flip flops can be used in counting. So now one more thing before you go, you can draw out this mod A counter here in the state transition diagram. So we're going to start from 000. So at this point, you're supposed to start from 0. And this is before clock pulse. This is 0 in decimal. So we're going to start from 000, go up to 001, next 010, next 011, next 100, next 101, next 110, 111, and then we set back to 000 and keep counting. So this is a mod is counter state transition diagram. Thanks for listening, and I hope you understood.